Hi, dear all. Good afternoon. Good afternoon. My name is Young Chifai. I'm a associate professor at University Technology Malaysia. I will be moderating this session today, and I'd like to welcome you all to join our 39 distinguished lecture series organized by Faculty of Engineering, University Technology Malaysia. Every week, we will bring you some of the top professors and researchers around the world to share with their research work and findings. And today we are really fortunate to have Professor Chenguang from University of the West of England, Bristol, United Kingdom. And right now we are late afternoon at 4 p.m. and Prof. Chenguang has to present at 9 a.m. in the morning, so it's at a different time zone. In fact, Prof. Chenguang is a personal friend of mine. We know each other almost a decade ago at Imperial College London. He did his postdoc doing some very amazing stuff on robotic and human, and and really good to have him here today. There's a lot to learn from him. So at this moment also, myself and Prof. Chen Guang are exploring some of the project together to look into robotics between United Kingdom, Malaysia, and also China. So this will be a very exciting time for us. So we are exploring a lot of collaboration. And today, Prof. Chenguang's topic will be on human-like robot control design and also human-robot skill transfer. And he has published a lot of very good publication, and you can really look at him. And the session will be around 30 to 45 minutes of presentation, followed by about 15-minute question and answer until at 5 p.m. And really, if you have any question, feel free to write your question on the Facebook comment. And right after the end of the presentation, we will pick some of the question and then to ask Professor Chen Guang on some of the question that you want to ask. Yeah. So please write your question if you have any. And before we start the session, let me invite Professor Dr. Muhammad Rafiq, our Dean of Faculty of Engineering, University Technology Malaysia, to say a few words to welcome Prof. Chen Guang. Prof.
Thank you, Chefai, for moderating the session. Assalamualaikum. Hello, welcome everyone. Welcome to our 39th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today, it is my utmost pleasure to welcome Professor Chenguang from the University of the West of England, United Kingdom. A bit about our presenter today. Chenguang is a professor of robotics at UWE Bristol, the leader of Robot Teleoperation Group of Bristol Robotics Laboratory, a co-chair of the Technical Committee on Bio-mechatronics and Bio-robotics System, B2S, IEEE Systems, Men and Cybernetics Society, and a co-chair of the Technical Committee on Collaborative Automation for Flexible Manufacturing, CAFM. IEEE Robotics and Automation Society. He received his PhD degree from the National University of Singapore, NUS, in 2010 and performed postdoctoral research at Imperial College London. He is the recipient of the prestigious IEEE Transactions on Robotics Best Paper Award as the lead author and over 10 Best Paper Awards from top international conferences. He has been awarded the EU FP7 Marie Curie International Incoming Fellowship and EPSRC Innovation Fellowship, as well as EPSRC First Grant. He serves as associate editor of a number of leading international journals, including IEEE Transactions on Robotics. His research interest lies in human-robot interaction and intelligent system design. So that is a brief biography of our speaker. Here now is Professor Chenguang from the University of the West of England with his talk entitled Control Design and Skill Learning for Human-like Robot Performance. Professor Chenguang, over to you.
Thank you, Professor Rafi. Thank you, Chefai, for the introduction and the invitation. It's really my honor and pleasure to give this talk to share my recent research progress on the topic of control design and skill learning for human-like robot performance. Yeah, my name is Chenguang. I come from Bristol Robotics Lab. Yeah, thank you. Okay, please let me start to talk about my research. Okay, at the beginning, I would like to briefly introduce our university and our lab. So as mentioned, our University of the West of England is located in the city of Bristol, just near the Bristol Channel on the west coast of England. Our university has more than 3,000 staff and about 30,000 students. And we host the largest interdisciplinary research center on robotics. In the UK, we have two nationwide large robotics research center. One is in Edinburgh, another one is in Bristol. And our Bristol Robotics Lab is the first established robotics research center and the largest in the UK. We have over 300 academic staff. In our Bristol Robotics Lab, we have about 20 different research groups. For example, we have the group on machine vision, we have group on swap robotics, and we also have a group dedicated to surgical robotics. And personally, I'm in charge of the robot teleoperation group. Well, today my talk will start from the background introduction, and next I will talk about two topics which are closely related to each other. One is from control point of view, how to implement human-like behavior on robots. Another one is how to transfer the manipulation skills from human demonstrator to the robot. Let's start from the background. Why we need so-called physical human-robot collaboration. As we know, from the manufacturing point of view, traditionally we have, for example, manual assembly line, which is of course of low productivity because of low speed and low efficiency. To improve the productivity, we introduced so-called robot test manufacturing. But for the assembly line with robots, we have to pre-program these robots. While towards Industry 4.0, we need a more personalized, customized product. That implies we may need to reconfigure the product line from time to time. For this high variety, low volume products, we need more flexibility because robots are pre-programmed. If you need to reconfigure the assembly line, you have to reprogram the robot, and you may need to reconfigure the whole product line, which is quite time-consuming and costly. Well, on manual assembly line, we don't have such problem. If you give a new command to the workers, they can quickly adapt to make something new. Therefore, it seems we as human workers we have very high flexibility, while for robots the advantage is high accuracy, high repeatability. Okay, so it seems a straightforward idea if we can combine the advantage of humans' flexibility and the robots' efficiency. That's why it's a hot topic to study human-robot collaboration. Okay, as we know, the first industrial robot was introduced in the United States in 1950s. In early ages, robots were used for motion control tasks, such as soldering. For this kind of task, there is no physical contact between the robot and the object or the environment. So the only concern is the accuracy of the motion. So motion control will do all the job. Well, if you need the robot to interact with the environment or interact with human, there will be contact force. Therefore, we need to consider force control. So the so-called hybrid motion force control was introduced. For example, if we use a robot manipulator to clean the window, you have to maintain a proper force on the normal direction against the glass. While you can plan the motion to move on the surface of the window on the tangent direction. So this kind of techniques, you control force on one dimension and control motion on the other dimensions. It's called hybrid force motion control. Well, if you want to regulate both force and motion along the same dimension, we need so-called impedance control technique. And this impedance control was first introduced in 1985 by Professor Hogan, which will be also mentioned later. Well, recently, more and more researchers start to study how do we control the robot to demonstrate more human-like behavior. Therefore, another hot topic of recent study is how do we use biosignal to enhance the control performance on robots. Well, my research interest is to enable robots to perform like a human. For this purpose, one method is that we can try to model the control mechanism from a neuromotor control point of view. We can do a lot of study on human subjects, how our human neuromotor system controls the muscle exoskeleton to perform interactive tasks. We can use human subjects to do the experiment, collect the data from the experiment, and then we can use control theory such as adaptive control, learning control to model the control mechanism which the neuromotor system use for human control performance. And then we can modify these models to implement on the robots. In my research, I also use a lot on the electromyography, especially the surface electromyography signal. That is because for interactive tasks between robots and the environment, you can measure the contact force, use force sensor, right? But it's quite hard to measure the stiffness, especially from our human's limbs, because we don't have any sensor that can directly measure stiffness. But electromyography, this signal which reflects the activation of the muscle, it actually gives us a chance to estimate the stiffness and even force from the energy of the signal. We can do filtering and then detect the envelope of the filtered EMG signal, and then we use this signal. We can do online estimation of the stiffness of the human limbs. Okay, so based on this background technology, I will start to introduce the first topic on the compliant control design of human-like robot performance. As mentioned before, impedance control is a quite popular technique in robotic control. So what is impedance from mechanical engineer point of view? Impedance is a model of inertia, stiffness, and damping, as shown on this right-hand picture. If, let's say, if you hold a cup of water, you use your hand. Let's say if someone give you a disturbance, you will be disturbed and deviated from your original position. But because of the elasticity of our muscle, we will be able to restore back voluntarily. You can restore back. So this kind of elasticity is the property of impedance. You can imagine as if there is a spring connected between the original position and the disturbed position. So we are interested in the stiffness modeled by the screen and the damping modeled by the damper. Let's suppose our motion is on the XY two-dimensional surface. On this two-dimensional plane, the K, stiffness K, is a 2x2 matrix. In order to visualize this 2x2 matrix, we can plot it as an ellipsoid, as shown on the right-hand side. You can plot inertia, stiffness, and the damping. All these three are 2x2 matrix. You can plot them as an ellipsoid, so you can visualize the value along different direction. The father of impedance control, Professor Hogan, in 1985, when he introduced impedance control, he actually proposed a hypothesis that our central nervous system will be able to regulate the contact force on the end effector. From our human limb point of view, end point means the wrist. If excluding hands, the end point will be the wrist joint. So the hypothesis is that we will be able to adapt the force, contact force, and impedance independently for different tasks. That means they are not coupled. We can decouple. We can decouple them and control them independently. This was not experimentally proved until 2001, when our supervisor, Professor Bodai, published his Nature paper. He reported his experimental result. He used a human subject, and the human subject is supposed to move along a straight line from the start point to the target point within a force field unknown to the subject. So in the experiment, we suddenly add in the force field while the human subject has no knowledge beforehand. He used two force fields. One is called divergence force field. As you can see on the left-hand side, the force field is pointing to two directions. If the human subject's hand is slightly deviated to the left, the force field will push for the left, otherwise push to the right. While in the other force field, so-called VF, the direction of the disturbing forces are basically along the same direction. So as we can see, at the beginning, the human subjects tries to follow the straight line as shown in the green. It's not quite straight, but roughly it's following the straight line from start point to the end point. Well, when the disturbance force is added in, as we can see in the right line, the first column from the left, the subject's hand is deviated to either left or right, no longer be able to follow the straight line. But after a few trials, as we can see, the human subject is able to restore back to the straight line. And in the catch trials, that means when the subject suddenly the force field can be withdrawn without knowledge of the human subject. In this case, in this catch trials, the human subjects move even more closely follow the straight line. So from the first column, the disturbed trajectories to the restored straight lines, we see there's something happened in the neuromotor control system. It seems the human subject will be able to learn to adapt the control strategy in order to compensate the effect of the disturbance force. Similarly, for the situation in the VF force field. So what happened during this learning process? So because the adaptation of the control strategy, there must be a learning process. After data analysis, we see in the DF force field, the force does not change. It's just a very slight difference as shown on the bottom left. On the XY direction, the force, contact force, as you can see from the green line to the right line, there's very slight change. While the stiffness, there are significant changes on the stiffness, as you can see from the green ellipsoid to the right ellipsoid. They are elongated along the direction of the unstable direction. For the DF, the horizontal direction, which the human's hand will be disturbed, is called unstable direction. As we can see, all the ellipsoids are elongated along this direction. While for the VF, we see the stiffness ellipsoids does not change quite a lot, while the force, the force changes a lot. So in these two different scenarios, in the first scenario, the human subjects do not change force. Instead, they use increased stiffness to compensate for the force field. Well, in the other scenario, the stiffness does not change a lot, while the human subject try to use force to compensate. So in summary, for the unstable, which also means unpredictable force, we human neuromotor system try to use stiffness regulation or stiffness control. While for more stable force field like VF, the direction is predictable. We do not need to increase stiffness. Rather, we use force to compensate for the disturbance. Another experiment done by Chief Musa Ivadi used similar technique, but he created two force field within circles, a large circle and a small circle. The force is pointing from the center of the circle along the normal direction to the upside. So similarly, the human subject is moving along the straight line, but the force will try to push the hands upside. The force is created by a vortex spring, and the stiffness of the vortex spring was increased from 200 Newton meter to 2000. When the stiffness of the vortex spring is increased, we can see the adaptation, the change of behavior of the human subjects. At the beginning, when the stiffness is quite low, that means the force field, you will feel it very soft. In this case, the human subject try to follow the straight line, as if there is no force field. While if you gradually increase the stiffness of the vortex spring force, we can see the human subject, the motion trajectory is more compliant, will try to follow the curvature of the circles, either for the large circle or small circle. And if we suddenly withdraw the force field in the cat trials, we see the human subject did not restore back to the straight line immediately. Rather, they tend to follow the learned curved trajectory in the cat trial when you suddenly remove the force field. So what happened from control point of view, in the absence of the force field, if you still follow the curved trajectory, that means the reference trajectory of the control system has been modified or adapted if we think this problem from control design point of view. Therefore, from the above mentioned two experiments, we hypothesized that our neuromotor system are able to adapt force mainly for feed-forward compensation and impedance and reference trajectory. Therefore, we propose a learning controller to mimic the human behavior. In order to enhance the performance, we also define a cost function, and we use optimization technique to minimize the cost function in order to develop the learning algorithm. How do we adapt trajectory? How do we adapt stiffness and impedance in the presence of the contact force? That's the algorithm we developed from the optimization. Okay, so to test our controller, we first test it in simulation. In simulation, we create exactly same force field for the large circle, small circle in the divergence force field and the VS force field. So in all these experiments, we see our algorithm demonstrates quite similar behavior as what we have observed from the human subjects in the experiment. And then we implement these models in the physical robot. First, we test the algorithm on a very a simple 1 degree of freedom robot. This robot is driven by a variable stiffness motor, which is quite different from the conventional motor. Because it can produce both torque and stiffness. Actually, there are two motors in this actuator. One is to produce torque. The other one is to tune the stiffness of the spring in between the load and the shaft of the motor, so that you can change the stiffness of the spring. So we put a payload to this motor, and we see at the beginning it cannot reach the target, but after a few trials, it is able to increase the. Now we remove the payload, and we see there is some overshoot. But after a number of iterations, it will restore back to the target. And even if you give it a disturbance, it will be able to increase stiffness to compensate for the disturbance. In the second experiment, we use a 7 degree freedom KUKA-EVA robot. We manually give disturbance on the vertical direction, and it will stiff up along this direction, while keep compliant on the other direction. the robot will only increase stiffness. It will only stiff up along the direction when the disturbance comes. Even if you give disturbance on a diagonal direction, it will keep compliant on all the other directions. As you can see from the data collected from the experiment, the stiffness ellipsoid is only elongated along the direction when you give the disturbance. And we can also put a payload. The robot will try to learn how to increase the feed-forward torques in order to compensate the gravity of the payload. We also use these techniques for the insertion task. Similarly, we use a KUKA-EVA robot in this experiment. We compare our algorithm with the traditional algorithm with fixed impedance. So in our algorithm, the impedance is adaptable. So as we can see the result on the top right, by using our algorithm for the insertion task, the performance is much better in the sense that we can see when we insert this needle, using our algorithm, which highlights the result highlighted in the right, we see the hole is quite small and the surface is smooth. And if we use the conventional fixed impedance control, we see the break on the surface is significantly larger than our algorithm. So our adaptive impedance performs smoother and better than the previous method. So this work was published on the IEEE Transactions on Robotics, and in this paper we first propose a learning circle from human to the robot and from the robot to in order to provide assistance to the human, and we won the Best Paper Award for this IEEE Transactions on Robotics. The adaptive impedance control we proposed is not only suitable for interaction between robot and the environment, it can also be applied for the interaction between robot and human collaborator. For example, in the next experiment, we are going to show the physical collaboration between human and robot for a solving task. When we collaborate with another one to, for example, solve a piece of wood, we need to detect the intention of our collaborator. For example, when he is stiff up, we may need to relax our muscle. We need to match the impedance with each other. If we do not match, we cannot cooperate efficiently. In the next experiment to show, we use the mile armband to measure the surface electromyography 8 channels from human partner's arm, so that the robot will understand the muscle activation of the human partner. To solve a piece of wood with a single arm is not easy, so we use a robot to assist this human. We we attach a ATI 6-axis force sensor to the end effector of the Baxter robot arm. An admittance controller is implemented on the Baxter's robot arm, so that it can follow well the motion of the human partner. You can change the motion frequency, you can change the range of the motion. The robot can follow well, but that's not enough. We want to optimize. We want to optimize the efficiency. That means we want to save energy and maximize the performance. So the robot actually adapts the parameters of controller according to the muscle activation measured from the human partner, which is measured from the, as you can see, the white armband, which measures 8-channel EMG signal. From the data analysis, we can show that in comparison to the fixed controller, our adaptive controller is able to minimize the energy used by the human partner. And the cutting surface using our algorithm is much better than the result without our algorithm. That means use a fixed controller. As you can see, the surface was not smooth if you do not adapt the control parameters, impedance parameters. We also studied how to adapt impedance not only at the end effector's task space. We can also adapt the impedance at the drawn space. So we propose so-called hierarchical control. For example, when the robot is interacting with the environment, the priority should be the impedance in between the end effector and the environment. That's a priority. Well, for each joint, we can also regulate the impedance. We can make them stiffer or keep them compliant. Suppose that when the robot is doing a task, we human collaborator, we may walk around the robot. So there may be some potential collision between our human's body and the robots. So in most of the time, we try to comply. We try to keep the joints compliant, such that even if in the worst scenario, when the robot bump into our human body, if it's quite compliant, we can make sure we human are not hurt. This is from a safety point of view. Another advantage to keep compliant is that you can save a lot of energy. So in the controller design, the priority is for task 1 for the impedance at the task space, and the second level of objective is to keep compliant in the drawn space. So we try to decouple the space into 2 spaces. One is for the end effector in the task space. Another one is in the drawn space. Because the manipulator we used is a 7 degree of freedom, which it has kinematic redundancy. That means the 7 is larger than 6 degree of freedom in our Cartesian space. So we have null space. In the null space, we can do a controller design to make the motion in the drawn space compliant. So in this experiment, we use a Soya robot, which was made also by the Resync company. It's a next generation of a Baxter robot. And at the end effector, we also use the ATI force sensor. We test the algorithm in a number of different scenarios. At the beginning, we keep the end effector at a set point. That means we keep the position of the end effector to make the end effector motionless. And we implement compliant control in the joint. So when the human has compliance in the joint space, and in the second scenario, we move down, follow a sinusoid signal along the vertical direction. At the same time, we try to disturb the robot in the joint space. Okay, let me move the next topic on the skill representation, the learning, and the generalization. So in the first topic, we try to demonstrate a human-like behavior on robots from control design point of view. Next, we will do the research from learning point of view. We will try to capture the skills from a human demonstrator and use a number of techniques for the robot to learn the skills, manipulation skills from the demonstrator. In our, there are a number of different approaches to model the skills. For example, using the hidden semi-Markov model from statistic approach, while we try to use the method so-called dynamic movement primitive. Basically, it tries to use a dynamic system to model the trajectory, to build a parameterized trajectory. If you just record the motion trajectory and the force trajectory, you have a large number of sample points. But if you use DMP, you only have very few number of parameters, 3 or 4 parameters in the model. You can use this model to represent a trajectory with thousands of sample points. It's not, if we just record the motion trajectory and model the motion trajectory and reproduce, that's not enough. When we teach the robot, we would like the robot to be intelligent, to be able to generalize the skill. For example, we teach the robot to lift up a bottle of water. And the next time, for example, when we teach the robot, the bottle is only of half bottle of water. And the next time when the robot do the new task, it's a full bottle of water. If the robot do not generalize the skill, the task will be failed. And if the robot is able to generalize the skill, it will understand how to use more forces to do the new task. Similarly, on the left, let me show the video. We teach the robot on the video on the bottom left. We teach the robot how to put a blue block into a green cup. And we teach the robot a number of times because as human, we may make mistakes. So we teach a number of times. We use a Gaussian mixed model to combine this teaching to make sure the robot learns the best result. So of course, the robot can reproduce the motion. It can place the blue block into the green cup And the next time we change the location of the green cup. We move it from the up corner to the bottom corner. And after detection of the new location of the target from the camera, the robot will be able to replan the trajectory. And it's all automatic. And even if when the robot started the motion, you change the target position, you move the green cup from one point to another one, it will automatically replan the trajectory in the move and make sure it reaches the correct destination. So all this happens automatically. The algorithm is able to automatically tune the parameter in the DMP model, so the robot can make sure it reaches the new target. While the experiment mentioned before is just for motion control, we are more interested in the task with contact force. So we have to use force sensor and stiffness regulation. So in order to estimate the stiffness, we use EMG signal as mentioned. So we do some calibration beforehand the experiment. We build a mapping between the EMG signal and the stiffness. So, and then we use a pair of DMP model, one to model the motion, one to model the stiffness. And as we know, the stiffness of our limb, it not only depends on the muscle activation, and it also depends on the posture. So we have to calculate the Jacobi matrix. And in the calibration, we have to use the robot to produce some mechanical impulses to test and calculate the stiffness to fit a second-order system, and then we can build a mapping between EMG signal and the mechanical impedances. So when these are all ready, we will be able to estimate the stiffness online. As shown in the next experiment, we teach the robot to for the plug-in task, plug into a socket. If we just teach the motion to the robot, even the robot can reproduce the motion 100% accurate. As we can see, it may fail the task because the robot does not know how much force and stiffness it should use for this insertion task. For this kind of task, motion control always not enough. You need to apply proper force and maintain a correct stiffness in order to insert plug into the socket. So we use a dual arm teaching by demonstration interface. The right arm will be able to provide force feedback to the left arm, which is connected to the human demonstrator. And the human demonstrator also mirrors the EMG signal. So in the presence of the force feedback, the human demonstrator would know how much force and stiffness he should use to complete the task. And as you can see, we actually use two armbands because the MU sensor in the armband the joint angles, so we can calculate the Jacobi matrix. Okay, so finally the task was successful when we for the plugin. We also do the similar task for the cutting, for example, to cut a cucumber. You can cut a potato or cut an apple. You have to also to generalize. We compare with fixed controller with either low stiffness or high stiffness. And as we can see, using our algorithm with the variable stiffness to mimic the muscle activation from the demonstrator, the cutting performance is best because it's smooth and it's efficient. As we can see, next time we change to cut a different cucumber, and our algorithm will be able to adapt the parameter to generalize the skill, so it can cut different cucumbers. Another topic in teaching by demonstration is that we need to do segmentation of skills. For example, in this demonstration, we show the robot how to lift up a bottle of water over the obstacle to the other side. We can define 4 different stages. For example, stage 1 to reach the bottle, stage 2 to lift up the bottle, and finally we reach the obstacle and over the obstacle to the destination. We divide the task into 4 different 4 subtasks. So for each subtask we use a DMP to model the skill. The advantage to divide into subtasks is that if something changes, for example, if the obstacle changes to a higher one, you only need to modify the trajectory of that particular subtask. You only need to adapt the DMP parameters for that particular subtask. I will use another experiment to show why we need a segmentation. For example, we teach the robot to write Chinese characters. There are thousands of Chinese characters. You cannot show the robot each one of them Chinese characters. If you just teach the robot to write a few Chinese characters, and the robot will try to decompose the Chinese character into each different strokes, then the robot will try to recombine these strokes to write something completely new, but keep the writing style of the demonstrator. For example, in this result, the first 2 lines were written by the demonstrator, with demonstrator hand in hand teach the robot. The next 2 lines were written by the robot itself, and never taught by these characters were never taught by the demonstrator. The robot figure out how to write each stroke and then recombine this stroke to write something completely new. Okay, so in summary, so we propose a framework for the skill modeling and representation modeling and learning and generalization. In the recent publication, in addition to stiffness and motion, we also model the force trajectory, and we build models between the correlation of all these 3, so we can reproduce all these 3 elements at the same time, from demonstration, segmentation, alignment to generalization. That's our general framework. So we also try to use robot as a medium to transfer the skill from human to another human, from tutor to the tutee, for example, because we were able to transfer skill from human to the robot. So we want to extend our research to further transfer the skill from the robot to another human. Let me show the result. We have 2 students, one from China, one from Iraq. The Chinese student tried to teach the Iraqi student how to write a Chinese character. They are coupled from the dual arm of the boxer robot. So these 2 robot arms were virtually connected through a virtual spring damper system. So this research we think would be quite useful for applications such as rehab, because therapists, one therapist need to spend a lot of time with a patient for repetitive tasks. If we model the skill of the therapist and transfer to the robot, then the robot can provide guidance to the therapist for repetitive tasks. Again and again, do the same thing, repeat the exercise. So this will free the time of the therapist, and the therapist can spend time for another patient. So in the experiment, after a few trials, the tutor will be free, and the student will be purely guided by the robot to repeat the writing for the exercise. Okay, after about 10 times of writing, finally we test the learning results. And after this learning, we see the writing skill of this Iraqi student is much improved. And our algorithm with haptic feedback to the tutor with EMG-based variable stiffness, these techniques perform best than other fixed controller. Okay, that's end of my talk. Thank you very much for all the audience, and I would be happy to answer any questions from the audience. Thank you.
Thank you, Professor Chenguang. Thanks. It's a very amazing and interesting topic that you have shared, and it's good to see that there are other ways to write a control and beyond that. And I have some question here. Maybe I will start to ask a few first. And there is an audience asking from Muhammad Al Mola. Is asking that, is it robust to external disturbance?
Sorry, can you say again, Chofai?
Is it robust to external disturbance? For example, I think you were mentioning you use impedance control to control the robot. And then you were using a different kind of method to train the robot to learn and to perform some tasks. But let's say there is other noises and disturbance by external. Is it robust into this kind of disturbance?
Yes, our controller are not only optimal, we are also robust. As shown in the videos, we disturb the robot manually. We give a lot of disturbance to the robot. For the external disturbance, no problem. Our algorithms are robust, and we are also robust to the noise, for the measurement noise.
Okay, interesting. So let's say it has a lot of benefit. For example, like you mentioned, it can actually the external disturbance will not really affect too much of the impedance control. So back into the question, I mean, right now, why a lot of industrial robots are still not using this kind of control? What are the challenges? What's stopping them to use this new way of control? For example, the impedance control and learning.
Actually, for example, for KUKA, they are introducing compliant control, so-called next generation of collaborative robots. You see a lot of new robots like KUKA EVA, like ABB Yumi. They are now integrated with this impedance control function. While for the traditional industrial robot, I think a number of reasons why there were no such techniques. One is the force sensor is quite expensive. Another one is traditionally the robot is working behind a safety cage. It's separate from human beings. They don't use human-robot collaboration. The robot just do the motion control. It's pre-programmed, just repeat the motion. As long as they can guarantee the accuracy of the motion, the task can be done. But now we want to study how humans and the robot can share the workspace, how they can work together using collaboration to combine the flexibility and the efficiency for the production. So in this case, we have to make sure the safety of the human partner. That's why we need compliance on the robot more urgently than before. And another reason is that we want the robot to do more delicate tasks than before. Conventionally, we use robot only for motion control to do such soldering, welding. But now we want the robot to do more intelligent work, like our manual assembly, like the task I've shown in the video, to do the insertion, like plug-in task. This kind of tasks were not done by the robot before, because it's quite hard. So if we want to apply the robot to more complicated, more complex tasks, we have to study impedance control, especially for the force interaction between the robot and the objects.
Okay, interesting topic. So, I mean, UWE Robot is one of the leading collaborative robot in the global right now. So what is the difference between Universal Robot and KUKA, Libya? What kind of method they are using? Are they similar or they are different?
I think a major advantage of KUKA EVA is that you can access the low-level torque control. While for UR robots, they do not allow you to touch the low-level controller. You cannot do any force control. You can only use the interface they provided for the motion control.
Okay, interesting. So there's a question from the floor. Kasim Hamad Shurid, him asked, to make connection between robot and human, which type of connection is the best? Wire or Wi-Fi or Bluetooth or mobile communication?
It depends on your combination. In most of our experiments, we use Ethernet for the communication between the controller, the PC, and the robot. While we also, of course, we also use the Bluetooth. For example, the armband we use to measure the EMG signal from the human demonstrator. It is communicating with the PCs through Bluetooth.
Yeah, I think the answer is really depend on the application. What is it for? If you need better bandwidth, then you need Wi-Fi. With short range, then you can use Bluetooth. Yeah, that's
exactly.
And that another question that I have is a very general one. I think you are a very, very global researcher. I mean, you're from China, then you went to Singapore for your PhD, then you were in Imperial College London doing your postdoc, then you become a lecturer in UK, then you travel, now you are a professor at Bristol. So can you give a perspective of a robotic research in terms of South Asia, I would say Malaysia and Singapore, then in China, because China itself has a huge research in robotics, and also in Europe. So what do you see the trend, similar trend? What do you see the differences between these three regions?
Yeah, I think the research of robotics is quite popular worldwide, no matter in which country. It's very hot in China and in the UK. While the focus or the application maybe a little bit of different. In China, I see the government invested quite a lot of money for the manufacturing, for robotized manufacturing. They want to upgrade the manufacturing, and they want to replace human labor with robots. While in the UK, I see things are a little bit different. The government is more interested in the healthcare technology, how to use a robot for elder care, for disabled people, and to upgrade the hospital. I think they have a different concern on the application of the robot.
Yeah, okay, thanks for that. I can one or two more questions if there is anyone. Otherwise, I'm going to ask from my list. So COVID-19, again, I don't think we can miss this one. COVID-19 has hit us hard globally everywhere. So what do you think the direction of a robot in terms of the control and also the robot direction?
Yeah, from my point of view, yeah, I'm leading the teleoperation group at Bristol Robotics Lab. Actually, I think teleoperation will play a major role in the future, especially in the hospital, to avoid contact between the patients and the doctors. So I think maybe in the future, we will use more teleoperation for diagnosis, for even for treatment. one of my recent research is on the using teleoperation for the ultrasound examination of the patient. We use teleoperate a robot to attach a probe on the end effector of the robot to scan the human body in order to avoid any physical contact between the patient and
you mean to scan the patient or to diagnose the patient whether they have a COVID-19 infection, is it?
It's not for COVID-19, it's just for physical examination.
Okay. So there is also to reduce the physical interaction between the doctor and so the patient. Yeah.
Exactly. To avoid any possible contact as much as possible.
Okay. I think I have one last question, and I think this is going to be you already answered a little bit on this question, but I want you to share it because this is going to be very helpful for the audience. So what is your advice to the audience? They mostly are the researcher and also lecturer and professor in robotic field. What do you think the trend and hot topic? I mean, let's think the three one. You mentioned teleoperation already. What are the other two, in your opinion, would be the very hot topic for the next, let's say, 3 years in robotics field?
Yeah. As far as I understand, in the UK, I think the government, the focus is on the healthcare. So one of the application I think is on the rehab robot, especially something like exoskeleton, especially soft exoskeleton robot, which is quite popular recent years. Yeah. As we know, soft robot is quite popular, especially one of the soft robot is called a Continuum Robot. It can be used, for example, the snake-like robot. It can be used for the inspection of the blades of the air engine. As far as I know, Rolls-Royce, they have, and even the giant company, Boeing, they have bought a company in Bristol called UWE Robotics.
Wow.
They bought a small company in order to provide the snake-like robot for the inspection of the air engine for Boeing company.
Wow, that is a very interesting success story. And yeah, I mean, I'd like to know more. I will have a chat with you there. So guys, just now Prof. Chenguang did mention about 3 hot topics. The first one is really about the teleoperation. The second is healthcare. And the third one is actually soft robotic. And the soft robot has some success story where Boeing actually bought over this small little company. And well, now we can see that research are really being commercialized. And we have one last question, I think, from Ko Kang Siang. So he asked, may I know what is the current challenge in teleoperation and what would be your future research focus? Maybe focusing on the teleoperation.
Well, so traditionally, the challenge for teleoperation is the stability problem in the presence of time delay in the communication channel. While now we have 5G, it seems the communication is much better. We can expect the time delay will not be a major issue. Well, another thing is the immersive interface for the teleoperation, because teleoperation is actually to transfer the human demonstrator's manipulation skill to the remote robot. We need to create a user-friendly interface such that the human teleoperator can perform the best, can transfer the best skill to the robot. If the interface is quite hard to manipulate, the human teleoperator may not even have to spend a lot of time to learn how to use the interface. The performance definitely will not be good. And because you are teleoperating a robot in a remote place, you have to feel as if you are with the robot side by side. So that means you have to provide a very immersive feedback to the teleoperator. That's what I'm quite interested, how to create immersive feeling to the and improve user experience for the teleoperation. I think that's a quite popular, it must be a quite popular topic for teleoperation in the near future.
Well, that is a very interesting point. I mean, I thought that you're going to say about the 5G, 4G, the communication latency and whatnot, but actually the interface is very important. The UX, IX, and so on and so forth. And there's one more last question. I think I'm going to ask this. There's a lot of questions coming up. And I think this is relevant to the previous question. May I know, since your research is leaning toward teleoperation, do you think augmented reality will be useful to be used together with teleoperation? This is a question from Mr. Ko Yeseng. And I think just now did mention about the UI, UX. Do you think the augmented reality can help on this matter?
Yeah, So the learning, the learning from human techniques I mentioned will be quite useful for teleoperation, because for teleoperation, one of the concern is how to reduce the workload of the teleoperator. If you manipulate teleoperate a robot to do a very complex task like a surgery, you have to spend hours concentrate on the task. You will be very tired. If for some repetitive task like knotting and suturing in the surgery, for the telesurgery, if you teach the robot how to do the task, the robot could do the repetitive task by itself, so it can reduce the workload of the teleoperator, of the surgeon. This will be quite useful. We've talked with the surgeons, and they are very interested if the robot can share the workload of the surgeon. This is quite interesting for telesurgery.
Okay. But let's say go a little bit detail. The question was asked about the augmented reality. Do you think this somehow help in the teleoperation in the teleoperation works?
Yes. Actually, we've done some preliminary work on teleoperation with augmented reality. It's quite useful to enhance user experience and to provide an immersive feeling to the teleoperator. It's quite useful, but it also depends on human, because most time we use the virtual glass.
Yeah.
Yes, some users they are not comfortable with that glass.
Yeah, that's right. I think the technology is still very new, but I think people are working into that direction. Like you mentioned earlier on, this could be one of the trend that people are looking into, teleoperation, and there's a lot of subset. And I think we are run out of more than 1 hour already. Once again, thank you very much, Professor Chenguang from the University of the West of England. I mean, today I learned a lot. I'm sure that the audience also learned a lot. And I'd like to take this opportunity to thank to all the audiences to stay with us and to listen to Prof. Chenguang. And at this moment also, myself and Prof are discussing on some collaboration. So if you are interested, you can drop him a line. He's more than happy to open for discussion for potential collaboration. And once again, on behalf of the Faculty of Engineering, University Technology Malaysia, we thank to Prof. Chenguang for his very interesting and insightful talk today. Thank you, Prof.
Thank you, Trifai. Thank you very much.
Thank you. Bye-bye.
Thank you for your time. Bye-bye.
Bye-bye. Thank you.
Bye.